Okay, let's start with our second video, which is basically the data representation of your hardware. So basically, we will learn how we store stuff in binary in your PC because your PC only understands 0 and 1 and that's it. We also will be learning how to convert to like hex. Well, not conversion, you have already learned that in the previous video. So over here, we will just like see why those matter and how like these three actually convert to each other, why they are needed or anything like that. And I hope these conversions make sense by this point. If not, please ask me about it. So yeah, a few things you have to learn over here is like a byte is sequence of 8 bits, which is basically something like, so this is 1 byte. Another representation of 1 byte is two hexadecimal digits, which is over here 0, and for 0101 is 5. So this one is a byte. So a byte basically uses 2 hex or 8 binary digits. So the fundamental unit of storage memory is byte, because whenever you mention your RAM, sorry, whenever you mention your RAM or HDD or SSD, you just say I have like 16 gigabyte of RAM or like 1 terabyte. So in both cases, you are using byte to represent how much storage you have. So yeah, that's why byte is still the fundamental unit of your storage in your memory. Another word or jargon we are going to use is nibble. We're not going to use it that much. So nibble is basically half a byte, or 2 nibble equals to 1 byte. So this is a nibble, this is a nibble. I hope that makes sense. So we know that our system has like finite number of storage devices. Like even like big servers have limited storage. Like if you use a Google Drive that is not provided to you by Virginia Tech, it has size of 15 gigabyte. You cannot use more than that. Even your hard disk has something like 1 terabyte, or your SSD has like 255 gigabyte. So as you can see, our storage devices are limited. And not just that, our memory is also limited. So we have to know how or why this limitation is important. Because like if you run out of memory, you cannot use the resource, right? With resource, I mean like RAM, GPU, HDD, whatever. So so we have to learn how to use the limited storage to store our finite number of numbers. So yeah, we can only represent a small finite number of bits for any integer value. We will see how much our limit is soon enough. So yeah, we also have to learn like how to do mathematics in the computer, right? So yeah, traditionally integer uses 32-bit. There was a time when integer only used like 16 bits, but now it's pretty much convention is going to use 32 bits. If you want to use more than 32 bits, there's like double, which uses 64-bit. And I think there's something like uint 64, in which case you will be using unsigned integer that is 64-bit. 64-bit, sorry. So yeah, this is how much space integer has. So the representation 2 to the power 32 is basically something like this. So if you have like 4, if you have like memory location of 4, so how you use it is something like this. So you have 4 slots over here. You can use either 0 or 1, 0 or 1, 0 or 1, 0 or 1. So you have a total number of 2 into 2 into 2 into 2, which is 2 to the power 4. That's how many numbers you can represent with this limited space. The same works for this. I'm not going to draw the whole thing, but basically there's like 32 slots and you can use 32 of them at the same time, which is how you represent integers, and that is precisely these many patterns. So you can represent this many numbers with your integer memory location. So remember in the assignments you face something like very big numbers or something like that. So the main reason it happens is because of how your numbers are represented. For example, if you're using sign bits, then you're going to use 31 memory locations, and the last memory location is going to be used for signs. If it is 0, then it's a positive number. If it's 1, it's negative number. So whenever you're using a normal integer, it's going to be signed. But if you're using something like a unsigned, then you're going to use all of the bits. So basically there's not going to be any negative. So if you have something like -2, 6, 5, it's going to be some sort of positive number in your unsigned. So whenever it rolls back, that's the number you're going to get, and it sometimes gets confusing because this number is so big you feel like this is a memory address, which is not. This is basically the unsigned representation of these numbers. And there's also the 2's complement representation, which we will be learning pretty soon. So yeah, data type, a collection of values together with definition of number of operations that can be performed with these values. I think that's pretty self-explanatory. We need to provide support for variety of data types. We already have support for int, double, float, character in C. There are other data types in other other programming languages, but these are the ones you need to be aware of the most. For integer values, we need to provide a variety types that allow users to choose based upon the memory consideration and range representation. So for contemporary programming languages, we would expect signed integers and unsigned integers. For example, int 32t, which is signed. If we are using uint 8t, that's an unsigned. We actually specify how many bits we are going to use. The common arithmetic operations work for all of them. It's pretty simple. And sensible handling of issues related to limited ranges of representation. In your CO5, you have seen how you can use typecasting to break through that, but you know how to use it. So I hope that assignment itself was pretty useful for you. Sensible handling of computational errors resulting from abuse of operations. Okay, so this one you have to take care of yourself, because whenever you're using int and you're converting it to uint, and if it's a negative, then it's a very weird number over here. So this one is on you. So unsigned integers, we store numbers in base of 2 using total in bits to represent its value. So there's not going to be any sign bits. We are basically using all of the 0 and 1s we can put in the memory location. So yeah, and another thing is n is usually 8, 16, 32 and 64. That's basically a power of 4. So 4 to the power, is it? I think so. That's 8. 4 to the power 3 is 16. 4 to the power 4 is 32. I can be wrong. I can be wrong about that. Yeah, I'm definitely wrong about that, I think. So yeah, they are usually power of 2, which is in this case 3, and so on. We use this to represent this of anyway. So the range of integer is usually this, from 0 to 2 to the power n minus 1, and that's usually for the signed, because that minus 1 is for the signed bit. So yeah, now we are going to see is how to do 2's complement. So for 2's complement, it's pretty simple. Okay, first of all, why do we need 2's complement? The idea of 2's complement is basically to convert a signed number from positive to negative and from negative to positive. So there's a very easy way to do it, and that is basically, first we represent it in a binary, then we just switch the bits. For example, 0 is switched to 1, 0 to 1, 1 to 0, 0 to 1, 1 to 0, 0 to 1, 1 to 0, 0 to 1. Yes, and then we just add 1 with it. So after we do that over here, sorry, I am running ahead. So after we do that, we get this number. So this number is basically the negative of this number. In this case, it's minus 40. Yeah, so this is this, and then after 2's complement, this one is minus 42. The reason it works, well, we'll see later, but over here, just to cross check, if we try to sum these two up, which is basically 42 minus 42 is going to be equal to 0, right? Over here, if you do it, you say that is going to be a 0. We are always going to ignore the carryouts for this place. So yeah, in this case, we see that 42 minus 42 is equal to 0. So we can see that the 2's complement works, right? So the question is, why does it work? So over here, we are going to give a very simple example. So this is 0, this is 1. So to have 0 from 1, we need a minus 1 of something. So how do we get that? So how do we get something which after summing with 1 turns into 0? So so over here we need to make sure that this one is 1, right? If we put 1 over here, it's going to turn into a 0, and it's going to carry over here, then it's going to be another 1, another 1, and so on. So in this case, we get this number. So from this, we want this number. How do we get that? The basic idea is 2's complement, because if we switch the number and do a plus 1, it just turns into this number. So yeah, to negate an integer with an exception, just invert the bits and add 1, and we can actually convert back over here by doing another 2's complement. The sign of integer is indicated by the leading 0. Remember, if it's 0, it's positive. If it's 1, it's negative. And integer itself is limited, which is by 32 bits. So if you have a carryover of 33 bits, you are going to ignore that one. So whatever number over here is, that's the representation of the sign of your integer. And for 0, there is only one representation, which is basically a whole lot of 0. And because the 0 itself is kind of like a positive, remember, it's not a positive, they are non-negative. Okay, so that's why in the maximum number of positive we have 0, and then we have this many numbers, and for minimum numbers we have this many. Because it doesn't have a 0, it has one more place for an integer. There's another shortcut for this complement. Well, honestly, in the exam you will not be asked to do this complement, I hope. If you are asked, I'm going to teach it to you again. But yeah, honestly, I like the version I have already shown to you, so I'm going to skip this. There's a 2's complement for base 10 as well. Do you really want to do that? You can just like, oh, okay, sorry. So this is not the one. So if the integer is non-negative, just expand the positional representation. So if it's a non-negative, so that means it's going to have a lot of zero over here, right? And then you just like do something like 2 to the power 11, and in this case 2 to the power 10, and in this case 2 to the power 8. You sum them up and you have the number. But if it was something like minus if it was something like 1 0 1 1, and imagine this is a negative number, then you have to expand it with ones, as it states over here. So it depends on how the number is represented. So if the sign bit, the one over here, if it's 0, it's going to be a positive number. If it's 1, then it's going to be a negative number. So representing a negative number from the binary is kind of tricky, because for positive number you could have just like done something like this, right? But for negative, it doesn't work the same way. So one thing you can do is like shown in the previous slide, you can do this to get the number. And if the number is negative, you just like negate the number itself. There is another way which is very complicated. Honestly, I don't understand it well by myself, so I should probably ignore that. And again, it's not going to be in the exam, so don't worry about it. So yeah, there's basic addition and subtraction in unsigned. So remember, if there's some sort of like negative number or something like that, the number is going to um, circle around. For example, you have like 42 and 42. If you try to sum it up, it's going to be this number, which is definitely not 84. I think. Oh no, sorry. This is definitely going to be 84. But if you are doing a summation and it goes beyond that number, for example, over here we have like 8 numbers, right? So it's going to be 2 to the power 8, which is basically 256. So our range is from 0 to 255. So if we try to go to 256, it's going to go back to 0. So that's why when we are trying to add 1 to 255, it just becomes 0, because there's an overflow. This overflow is going to be a very important topic in your 2506. So yeah, in terms of overflow, the basic idea is it doesn't have enough space to hold the carry out, so it's just going to go in a circle. So even though the number is supposed to be 256, in this case is just going to be 255 plus 1 equal to 0, because it doesn't have enough memory location to represent the number 256. In case of signed, it's usually going to be the same thing, but like in this case, again, we don't have enough space. So that's why when we're doing a negation, instead of from minus 128 to minus, it's turning into 120. Instead of turning into 129, it's going to turn into it's a positive number for some reason. Okay, the main reason why it happened was we are talking about signed over here. So in case of signed, in unsigned, we knew that it's going to be 2 to the power 8. But in case of unsigned, it's going to be 2 to the power 8 minus 1, because it needs one position for the 0 or 1. So it's going to be 2 to the power 7, which is 128. So over here, our range is from minus 1 128 to 127. If it goes beyond that, um, it's going to cycle. So in this case, it is going to turn into 127 instead of turning into minus 129. I hope that made sense. So yeah, you have been using this like int 32t or uint32t for a while now. So this number and this number are basically the same, even though their representation are different. So if you try to print it over here, it's going to print like I think it's going to print 128. I don't know. You can give it a try and try printing it, what happens. This one is going to normally print -1, but this one is going to print something else. So oh sorry, it's 32. So in this case, of course, it's not going to be -128. It's going to be this number, even though they are the same numbers. And if you try to do something like this comparison, it will say it's true, because in their base representation, both of them are represented like this: 1 1 1 1 1 1 1 1, and so on. And at the end there's a 0. So because these two representations look exactly the same, even though they are unsigned or signed or unsigned, they are going to say that they are the same number, even though over here you see that they are not the same number. It's just because of the difference of representation. So again, another thing, so for example, this is a int, this is a uint. So this one is a -1, this one is a 1, and if we try to do this, so it prints that x is greater than y. The reason that happens is whenever you're doing any sort of arithmetic operation, the int is going to be over here. When comparing signed and unsigned, the signed numbers are converted to unsigned. That's always the case. Int is always going to be converted to uint. So if you want to make sure that such conversion is not happening without you knowing about it, so you should do some sort of like some sort of like typecasting. So in this case, if you wrote something like x less than int 32t and y, then this x wouldn't be converted to uint, and in this case this one would be printed. Give it a try. So this is one way to get most negative numbers. So you can perform 2's complement operation like this. So there are memes about it, so you can write something like this or write like this just to show that you are more intelligent than the others, but it doesn't matter, they do the same thing. So this in this case, you are just like putting the 1 at the beginning of the number. In that case, this number is going to be it's going to be a negative number, right? Yeah, if you put the 1 at the top left, sorry, yeah, top left most, if you set the most significant bit as 1, is going to be this most negative number. So yeah, another thing that I have been mentioning since day one is ASCII numbers. So ASCII numbers are basically 1 bytes. So each number you are using, like each character you are using, they are basically ASCII codes. For example, this is 97, this is 98, and so on. Even your 0 is actually 48. So each ASCII numbers have their own version of integer representation, or even hexadecimal representation. It depends on how you're using it. So um, you know that in ASCII you can actually do something like arith- character arithmetic, which have been shown in the class a few times. Like you do something like a plus 1, it turns into b, and so on. This is pretty cool feature, and it is also available in most of the programming languages anyway. So this is the ASCII table, and this is the hexadecimal representation, because over here you can see that it goes till f. So one way to represent ASCII table is using hexadecimal, but I prefer the integer one, but it's up to you which one you want to use. For example, over here, if you want to know the hexadecimal of a, it's basically going to be from 441. So this is the hexadecimal representation of a, character a, and the small a is going to be 61, and so on. So hexadecimal, oh, sorry, ASCII table has been expanded later on, like, and later on we use like Unicode that covers all the languages, all the popular languages and their characters and everything. But like even now ASCII is the easiest way to work with if you're just working on English. But if you're using your native language, you can use Unicode, and usually Python just converts everything to Unicode, I think, but I can be wrong. You can look it up. Yeah. So these are some ASCII art. um, you can actually make this if you want, right? Yeah, that should be a good assignment, but like we are not going to make you do that. So yeah, the last one is Boolean logical values. So every single Boolean is basically 0 and 1, and they are of 1 byte. So basically there's literally 8 memory locations, and they are filled with 0 0 0 0 0 0 0 if it's like false, and there's going to be a 1. Well, if there's absolutely any 1 over here, it's going to be true. So using Boolean is basically waste of space, but this is the only way to do it anyway, so you have to use it anyway, whether you like it or not. I mean, you cannot just like save space by using 1 bit, because honestly you don't get to use just 1 bit. You always have to use byte, because remember, that is the unit for data representation. So this is the basic Boolean logic operation. Like if you do a and b, you are going to get 0 every time there's a 0, and only 1 when there's 2 1s. If you do or, you are going to get 1 every time there's a 1 in any of the sides. If both of them are 0, you're going to get a 0. There's also NAND, which is basically the opposite of AND. There's XOR, in which case if they are opposite of each other, it's going to be 1, and it's going to be 0 if they are the same. There's NOR, which is basically the opposite of OR, and XNOR, which is opposite of NOR. Sorry, my bad. Which is opposite of XOR. So I think that's it for this video. I hope you understood, and please come to my office hour if you don't understand any of this part. Nobody shows up in my office hour anyway, so that's kind of sad. But yeah, I'll see you later.